In the last lectures, we started a review of special relativity. In particular, we showed that the line element is invariant under Lorentz transformations. We will continue our review of special relativity in this lecture. To get started, let me review some nomenclature. For instance, we will talk about vectors, and by vectors, I basically just mean that these are objects that carry one index, for instance, A with the index mu. By contrast, we can think of other objects, such as scalars, which are things that don't carry any index at all. For instance, we can build scalars out of vectors by contracting the index. So basically, this is an object that is a scalar because the index mu out of these two vectors appears twice, so it's summed over. So this thing doesn't carry any free indices at all, so it's a scalar. We can also think about tensors, which are things that carry more than one index. An example of a tensor is, for instance, a rank 2 tensor, g mu nu, which has two indices, mu and nu. Similarly, a rank 3 tensor would be an object that has three indices. We can also think about higher rank tensors, such as a rank 4 tensors, r, mu, nu, alpha, beta, for instance, which is a rank 4 tensor. Obviously, this generalizes to arbitrary rank n tensors. A property of a vector is that for any 4 vector, we can write down the Lorentz transformation of the object simply by saying that if we do a Lorentz transformation, the vector a mu changes to the vector a prime mu, which is given as the Lorentz transformation matrix lambda mu nu contracted with the original vector a nu. Similarly, the vector a with index downstairs, recall that this is not the same as the original one because of the minus signs of the Minkowski metric. This one transforms as a prime mu with the Lorentz transformation matrix with lower and upper indices contracted with the original vector with downstairs index. Examples for vectors are multiple. Let me just mention a few. For instance, the coordinate difference dx mu, which is the 4 vector built out of the time increment dt and the space vector increment dx, this thing together is a 4 vector dx mu, and it transforms under Lorentz transformations according to this rule 4.1. Another example is the 4 gradient, which is the partial derivative d by dx mu, which carries the index mu upstairs. That comes from the fact that we derive with respect to an object that has an index upstairs here. And actually, this is wrong. This should be the index mu here should be downstairs, and that transforms as a vector as well. I will correct this in the slides. Another example is the 4 momentum p mu, which is built out of the energy E and the vector momentum p. That is also an object that transforms as a vector under Lorentz transformations. So far we have talked about vectors. Now let's talk about scalars. Scalars have the nice property that they are invariant under Lorentz transformations. For instance, if we recall that a vector such as dx mu transforms under coordinate transformations to lambda mu nu dx prime nu, we know, or we can calculate the Lorentz transform of the line element squared. The line element squared basically becomes the Lorentz transformation of the individual vectors dx mu together with the metric tensor. And this thing we have found in a previous lecture to transform or to contract simply to the metric again. So we get that the line element squared is equal to the metric tensor times the coordinate differences in the transformed coordinates x prime, and that is the same as the line element in the transformed frame ds prime squared. So what we find is that the line element is unchanged when you do Lorentz transformation, and that is a simple consequence from the fact that it doesn't carry any Lorentz indices, so this is a Lorentz scalar. Note that we can build scalars out of vectors. So for instance, we can take the contraction between two 4 momenta, p mu p nu. If we write it out in components, this is minus e squared plus p vector squared. And because we have contracted the indices between these two vectors, this object is a Lorentz scalar. We find that Lorentz scalar is invariant under Lorentz transformations. So this object in the transformed frame p prime mu p prime mu is the same as the original one p mu p mu. The object has a particular name. It's known as minus the invariant mass square. And we can see why this is because we know that it is a Lorentz scalar, so it's invariant under Lorentz transformations. So that means that we can pick any Lorentz frame that's convenient for us to evaluate the object. A nice frame to evaluate the object is the rest frame, where the momentum p just vanishes, and the relativistic energy is just the mass. So if we use that particular frame, we find that p mu p nu is just minus m squared, and that's the reason why it's called the invariant mass square. Obviously, because it's a Lorentz scalar, it means that this particular combination, the 4 momentum squared, is the same, it's invariant, in any Lorentz frame. Finally, let's talk about some properties for tensors. For a tensor, when we want to do a Lorentz transformation to a different frame, we have to put a Lorentz transformation matrix for every index that the tensor contains. As an example, let's take a rank 2 tensor. For instance, our metric tensor G mu transforms to the metric tensor in the prime frame by stringing together our original object G alpha beta together with a Lorentz transformation for every index. If the indices are down, then the Lorentz transformation matrices have to appear in such a way such that the indices that are contracted, which are alpha and beta, always appear one upstairs and one downstairs. And we have the two free indices mu and nu matching the metric tensor that we want to construct. Similarly, if you want to inverse metric with the upstairs component indices mu and nu transforms in the prime frame by stringing together Lorentz transformation matrices that have mu and nu upstairs so that they contract together with the original metric tensor in this form. It so happens that the metric tensor G mu is unchanged under Lorentz transformations. This is not the case for general tensors. In particular, if we do Lorentz transformations of other rank 2 tensors, such as the Maxwell field strength tensor F mu or the energy momentum tensor T mu, we find that they are not the same in every Lorentz frame. They change, and they change exactly according to the rule that comes from contracting every index of the tensor with respect to one of these Lorentz transformation matrices. Higher rank tensors then just generalize the transformation rule of the two tensors. Basically, every index gets a Lorentz transformation matrix. If we think of a particular rank 3 tensor, A, alpha, beta, gamma, then that transforms to the prime frame by stringing together 3 Lorentz transformation matrices that carry the indices alpha, beta, and gamma upstairs, and new indices rho, sigma, and tau downstairs that contract with the original symbol A, rho, sigma, tau. Finally, let me add a word of caution, which is that we will sort of eventually in the course we'll come across objects that look like but actually are no vectors under particular transformation rules. And basically what I mean by this is there could be an object A mu that carries an index, but it does not transform as a vector. So something that in the transform frame A prime does not transform according to Lorentz transformation matrix A nu. A stupid example of this would be an object that I string together by picking one element of one 4 vector and other elements of another 4 vector. So I've picked the energy and the coordinate. This thing has 4 entries, but it's not a Lorentz vector, even though I sort of wrote it this way. Note that this is less an issue for special relativity. Basically, I should not be allowed to write this combination with a 4 index mu because that tacitly sort of assumes that what I've sort of done is looked at an actual vector. But in general relativity, we'll be coming across things that sort of have these properties. They could be confused with vectors, but actually are not. And this concludes the present lecture.